Physics 3030, the universe. This is lecture 8. In this lecture, we'll be talking about inflation, cosmic inflation. And cosmic inflation was brought around to actually help fix a couple of problems that were known, called the horizon and the flatness problem. And then we'll show you how inflation fixes these. And the horizon problem has to do with this horizon picture, and this is the WMAP data of the cosmic microwave background, right? This is the CMB data. Okay. Now, the horizon problem really has to do with well, the horizon is as far as we can see, right? So that's normally, we all know the idea of what normal horizon is. But as the universe ages, okay, and it expands, the furthest out we can see from Earth in the center, okay, is sort of how far light has been able to travel. So, how far can travel in the age of the universe, okay? Since the speed of light is finite, okay, it can only have traveled so far since the beginning of the universe, and that's as far back in time as we can see, but that's also as far out as we can see, and that's the horizon. And the problem is, if I look at this picture, now remember this picture is kind of a smeared out, bent around picture of what would normally be a globe, right? So this end and this end are actually in contact with each other. They're really close to each other. So what I want to compare is something, say, in the center to something on the edge. And I'm looking, so something in the center compared to something on the edge is looking in two different directions, okay, from the Earth. And those ends are really far apart, okay? But the problem is they're really correlated. Now, this map, of course, sort of shows you the differences, but remember that those differences don't occur till the 5th decimal place. So up to 1 in 10,000 parts, they're almost exactly the same, and they're very, very correlated to each other. And so to 1 in 10,000 parts, those different ends of the spectrum are correlated to each other. Okay, so that means that they're correlated, and we can actually do the calculation, and we know that everything was in thermal equilibrium. So to 1 in 10,000 parts, right, to 1 in 10,000th of a degree, the universe at the time of when the CMB was released was in thermal equilibrium. Okay, and the problem stems that if I look at a photon from this region as compared to this region, and I go back and do the calculation, okay, it shows that those two different CMB photons, right, this distance, if I look back in time, they were like 90 million light years apart. Okay, but if they were 90 million light years apart, how could they be bouncing around, right? Remember, well, or I will let you know if you don't know, thermal equilibrium is really talking about molecules, okay, and it's talking about them bouncing around in each other, and it basically says that the average of the molecules is pretty close to what the energy of all these molecules are, because they're bouncing around with each other, and they all have the same type of energy, but they have to bounce off of each other to be in thermal equilibrium and to all know what the temperatures are. It's the same idea as if I bring two boxes, two cubes of metal, say, that are two different temperatures, and I just put them in contact with each other, right? Whatever the temperature of T1 and T2 are, they'll basically move to the average temperature. Okay, it's the same idea. Remember, temperature is just a macroscopic way of measuring what the motion of these little molecules is. And so they have to be in some kind of causal contact. We say causal contact, which means that they have to be close enough so that they can move at least, if they're moving at least the speed of light, they can touch each other. Okay, but the problem is if you go back in time, to when the CMB was released, it looks like the the universe, it looks like the furthest that these particles could have been apart was about 900,000 light years, which is a lot smaller than 90 million light years. So the universe is expanding at this early time, and we're going to do a little digression. Actually, let's do a little digression about what we're trying to talk about here. So. Okay, what I want to talk about is how it is that something that's only 300,000 years old, so at 300,000 years old, okay, the universe could have even been 900, photons could have even traveled 900,000 years. So that's what the calculations say. Photons from the center could have gone 900,000 light years. And this is because the universe is expanding. Okay, so let's go back to our pictures of the balloons. Okay, so we have a balloon and we have a little ladybug sitting on the balloon. Okay, and okay, I want to be really careful about what I'm trying to say here. You do the calculation, and you find out that the photons were 90 million light years apart. But in equilibrium. Okay. So they were in equilibrium, so that means they had some kind of causal contact with each other. The problem was that the universe was only 300,000 years old. Okay, so at first you'd think, well, that means that light could have only traveled 300,000 light years, and it actually could have traveled 900,000 light years. Okay, and that's in your book, and I want to explain why this part is the problem. So the horizon problem is that, and I'll show you why this 900,000 years actually could make sense, but the horizon problem is that the furthest that photons could have traveled is 900,000 light years, but we find out that those photons were about 90 million light years apart, but they're supposed to be in thermal equilibrium, and they can't be unless they were close enough to each other that moving at the speed of light they could have touched each other. Okay, so this is the horizon problem. Now I want to do a little digression here, which is how something that's only 300,000 years old, light could have traveled 900,000 years. And the reason for that is we're going to go to our balloons for the expanding universe again. Okay, and I'm a little ladybug. Okay, and I want to move from one side of one part of the universe to the other. Okay, so I'm going to go moving in some direction. Okay, and that direction is D. And say I'm a really fast ladybug, so I can move at the speed of light. Okay, well, of course, the universe is expanding while I'm moving. Okay, so I've gotten bigger over here, and as I've grown bigger, the spot I was going to is further away than it was when it started. And so because of that, this is where I was, and this is where I'm going to. Because it's expanding out from underneath me, I can actually move faster than, I can move a distance that doesn't quite seem to make as much sense with the whole speed of light being the speed limit. The speed of light is the speed limit, but it's the speed limit sort of in space. Okay, I can only move through the space through static space, space-time. Let's call it space-time because we'll get to the relativity in a little bit here. But I can only move through space-time at the speed of light, but then the space-time itself is expanding. It's like being on a walkway, moving walkway at the airport. Okay, it's moving underneath you, and the universe is the walkway itself, and it's expanding and it's moving out. And so I can move at the speed of light on the walkway, and I can move further than I normally would be able to. Okay, so that's why it's 900,000 years instead of 300,000 years. There's a little bit of a description about that in your book as well. But the whole problem is that 900,000 years does not jive with that 90 million years. Okay, and that's what the gist of the horizon problem is. Okay, and we'll get back to this, the next explanation of this in a second. Okay, and we can move to the next problem. So the next problem has to do with the curvature of the universe, and this is called the flatness problem. We haven't talked much about curvature. Okay, curvature. You know, a lot of you probably have ideas of what curvature is, and it's really all about general relativity, Einstein's theory of gravity. And there are all kinds of solutions to his theories, and we find that the universe should be one of these three cases, which there's a closed universe down here. Let's see, closed universe, a flat universe. This is closed. This is flat. And this is open. Okay, and this idea of whether the universe is closed, flat, or open has something to do with gravity, right? If I have a bunch of gravitational particles around, they all attract each other, and so they start to clump up. They start to clump up. So if I go to a next picture, I have some that are really close here, and some that are really close here, and some that are really close here. They all start to pull together. And if I look at the entire universe, right, if there was enough stuff in the universe, then after a while I would just end up in one big lump in the middle. And I'd go back. So I'd expand apart from the Big Bang and then come back to some lump. Okay? And that's what the idea of the closed universe is. It has to do with how much stuff's in the universe, but also the actual curvature of space-time underneath it. And then an open universe would just keep expanding. So this open universe keeps expanding. Okay? This one has what we call a big crunch, comes back. Okay, and this graph is the size. This is sort of time, and this is the size of the universe, right? So it starts at some spot, kind of moves up the way, and then at some point it starts getting pulled back together. The open universe just keeps expanding and getting bigger, and the flat is some perfect in-between, okay, where there's enough stuff where it doesn't accelerate apart like in the open universe, and it doesn't come back together. It just kind of like keeps coasting. Okay, that's kind of how I like to think about the flat cases. It keeps coasting. And there's something that your book refers to, and cosmologists refer to as the critical density. Okay, and this critical density really has to do with expansion and the breaking due to gravity, right? Which I was just talking about above. So gravity sort of pulls everything together, tries to slow down that expansion because it's all attracted to everything's attracted to each other. And doesn't matter too much, but there's something called omega, okay? And if omega is the critical density, if it's less than 1, then there's not enough stuff for gravity to really expand it. If omega is greater than 1, then the universe contracts. And if omega is exactly equal to 1, that's the flat case. Okay. Now, the problem is that it turns out that to our measurements, to a very, very close, the universe is flat. Now, this is a very special number, this critical density, and scientists do not like this. We're bothered by this idea that the universe, this one number, is almost exactly what it needs to be. And your book talks a little bit about where this thing had to have started. It has to be in like the 9th decimal place. So it could have been between 1.000, lots and lots of zeros, 1 and 0.9999999. So between those two numbers, which is pretty exact, and we don't like this. And so this is what's called the flatness problem. Okay, because it turns out the universe is flat, and we don't know why. Okay, in general, over the average of the entire universe, it is flat. Okay, and so we get to a gentleman named Alan Guth. And Alan Guth was actually a particle physicist, and he was trying to explain some problems with particle physics and theories about the Big Bang and what should have happened. And he came up with an idea that said, all right, maybe the universe went through something called inflation. Okay, and inflation, so first of all, inflation is a synonym for expansion, right? So this is something that happens all the time in physics that you need to be careful of, right? The expansion of the universe is just the regular old expansion from the Big Bang. Okay, everything gets blown apart. Regular old, I guess. Regular old expansion. Everything gets blown apart and is expanding. Inflation is something that is an exponential expansion, a really special time in the universe when we went through not just expansion, but let's call it uber expansion. And again, this happens all the time in physics. Words that we use colloquially as the same, so things like momentum or force or energy, those are very specific things in physics. And so when I say expansion, I mean one thing, regular old expansion. When I say inflation, I mean this very special time when we had exponential expansion. Okay, and there's a little bit of talk about what exponential means in your book, and I really recommend you taking a look at it. There's this old paradigm old parable about wanting a reward that was just on a chessboard, which many of you may have heard, which starts with 1 grain of rice on the first square, and 2 on the second, 4 on the third, 8 on the second. So you just keep doubling it over and over again. And this is exponential growth because it's 2 to the n, where n ends up being the number of squares on the chessboard. Okay, a lot of times you'll see e to the n or e to the x or whatever, where e is this special number. It's a little bit bigger than 2, and it's bigger than 2 and a little bit smaller than 3. Exponential growth is the kind of growth that we actually see this biologically, and population growth in a lot of countries is actually exponential. And I recommend you looking at some of the videos on exponential growth. Okay, but what I want to talk about is that this exponential growth can actually help the problems that we see, that we were seeing, the flatness problem and the horizon problem. Okay, so the first thing is, how does this, so what do we really mean by this exponential expansion? We mean that for for short periods of time. Okay, the distances, right? Distances would go from d to something like d times 10 to the 30. Huge, huge distances in really small scale, in really small amounts of time. So the idea was that I can go from this to this in, say, 10 to the negative 35 seconds, which is crazy. And if I look at how fast this expansion rate is actually way faster than c, than the speed of light. Now, how can that be? Right? Again, we say that the speed of light is how fast something can travel through space, time, and the universe is not traveling through space-time. It's just expanding. It's not light moving through space-time. It's just expanding. So these expansion rates can be huge. So that's what we're talking about. These e-foldings, we call them e-foldings because of that e in the exponential function, but huge expansion for very short amounts of time. And your book refers to something called a false vacuum. And the idea here is that, all right, if I was to draw something like this, the universe is sitting at some energy level here, okay? And the idea is that there's more energy than you think, because you think this is the vacuum because that's where you're sitting. But really, this is the vacuum down here, and basically there's a mechanism where this gives you more energy. You have, this would be some kind of energy scale of the universe, of what the energy universe has, and this is some maybe some time or some other part of some other parameter. But you're sitting up here and you have a lot of energy and you're using that to expand really quickly. It only lasts for a short amount of time, and then you quantum mechanically tunnel to this side. The details aren't important. The idea is that you just get this expansion really, really fast. Now, how does this help with things? Well, it helps with things is that if I look back normally and I see, okay, all of the molecules at some point, all of the stuff in the universe, all of the atoms and all the things that were there, say at the CMB, are about this far apart from each other. But that's too far apart, right? So too far apart for equilibrium. Well, if a little while before this, everything was way, way closer to each other, much, much faster than the expansion that we would normally think of just from the Big Bang, right? So this is the sort of expansion that we would think about inflation. This is some exponential expansion. And then, after this, we just have some low rate of expansion that we normally see, but it's really fast here. Okay, well, if it's really fast here, then back in this epoch, when we're starting, everything was still in causal contact. And then everything can be in equilibrium. And that's cool. And then the CMB comes along and everything was still pretty much in thermal equilibrium except for this tiny fluctuation, these tiny fluctuations in the 5th or 6th decimal place. And that solves the horizon problem because we were very, very close. And then we expanded really, really fast and there wasn't enough time for stuff to get out of equilibrium before the CMB happened. Okay, so that's the horizon problem. Fixed horizon problem. Check. Okay, and then we want to think about the other problem, which is the flatness problem. Okay, and the flatness problem, just start up here. Okay, is so the idea is that if I'm starting with something that is not quite flat, so what we want to think about is the problem is the omega equal to 1, right? We don't want it to be perfectly flat. We don't understand how that could be. And if it didn't start out perfectly flat, then we would have seen everything would have flown apart too quickly, or it would have already collapsed on itself. That's what all of our models say. Okay, and so the idea is we want to start with something curved. So say we start with something curved. Okay, start with some ball. And I'm looking at this thing and it's curved. Okay, now when it expands exponentially, right, and I start looking at the edge of it, all right, the curvature from here to here is really easy to see. The curvature from here to here is harder to see, and then when I get even bigger, right, the curvature of a piece of it is harder and harder to see. So you can see the whole thing is curved, but if I look at just this point of it here, it's really hard to tell that's not just a straight line. This is the same exact thing that kept us from thinking the Earth was round for the longest time, right? The Earth is round, but it looks flat to us locally, and it's because it's so big that we don't see it. Well, this expansion, this exponential expansion, it flattens space-time. Just in the same way that if I just blew up a ball really, really fast and I looked at an edge of it, it would be really hard to see that it was curved at all. Okay, just like the Earth. Just if I took a rubber ball and then made it the size of the Earth, it would be really, really hard to see that curvature. And so this fixes the flatness problem. And it turns out that, remember what I was saying about that false vacuum thing? That was a horrible picture. Let's try that again. The false vacuum is, I'm sitting up here and then I drop down to here, something like this. Well, when I go from one spot to a lower spot, I release a bunch of energy, and this also sort of points to where most of the stuff in the universe came from. So where most of particles came from. That release of energy, just like we were talking about before, if you have photons or something else, they can just boom, produce pairs. And this ends up being where most of the particles came from. That huge release of energy, remember, again, E equals mc squared, right? So energy is equal to mass when we're talking about really fast-moving things. All of that energy gets dumped into photons and protons and neutrons, and a lot of the particles that we see today are from inflation. They're all described by inflation. Okay? And one of the things that physicists work really hard to do is look for explanations of a mechanism for inflation. So a lot of particle physicists, a lot of cosmologists spend their time trying to figure out what were the mechanisms that got inflation to work out. And so there are a lot of different theories out there. Your book talks a little bit about them. I'm not going to go into too much detail on them here, but there are a lot of theories out there. We're trying to understand what was the mechanism that allowed inflation to happen and really caused this exponential expansion. Okay, and I want to just end here with a recap of what we talked about a little bit. I have one more neat picture here. This is a common picture. This is from NASA of sort of the history of the universe, right? And so we've gotten to the point where there's something going on here, the Big Bang, and then we have inflation where we have this super exponential growth. And then sometime after inflation comes and we have all that stuff we talked about last week, then we get the CMB, and that's the furthest back we can really see. So everything back here is sort of a big question mark. We know about particle physics and we can try and understand what's going on, but even further back we're not sure. We can't really see it, is the thing, right? We can't see what's back there. That's why we make particle accelerators, to try and figure it out. You see the CMB, the microwave background radiation is released, and then we have what's called the dark ages because stars haven't coalesced, and we're going to start talking about that, the first stars, next week. And then all of this galactic evolution as we move on. And this line here shows that, yes, the universe is expanding, and it's even accelerating, which is what dark energy is all about. But it's not anywhere near as exponential as this part is over here. Okay, and we'll come back to this this illustration again in the future, talk about different parts of it again. So, okay, thank you for your attention.